Another example for class 15, we're going to do a complete cycle here of a power plant with a turbine. I should point out this is a very important cycle and generally a little bit more complicated than this. We're going to do it on a per mass basis. They've given us some information here. I'm going to treat it maybe a little bit differently, but here are the things that we're looking for. We're going to look for the heat transfer in the line between the boiler and the turbine. All right, so we're starting out here at 1 and right here out of the boiler, and we're saying that there's heat lost, which is true. Generally, there's some really good insulation over this pipe, but there could still be some amount of losses across this. And then here we're going to find that how much work is extracted from the turbine between points 2 and 3. And then we're going to find the heat transfer to the condenser. All right, and on a ship, this condenser uses seawater, but you can also have like a cooling tower, which is a means of on shore of using like water dripping down to assist in the condensation of the fluid that is being used in the turbine and pump. Right, there's separate lines. Anyway, condenser takes it and removes the last bit of the heat of vaporization that from the fluid, the operating fluid, which is this water coming through here. And then we're going to have a pump that increases the pressure and also adds a wee bit of work into the fluid. And then it's going to go from 5 and then go through the boiler back up to 1. So we have ourselves a cycle. And you can see that this is a 2,000 kilopascal is the output pressure of the boiler, and just before the turbine it gets to 1,900 megapascals and about 10 degrees less in temperature. Then it exhausts to 15 kilopascals. So that's actually a vacuum, right? It's less than 101, so this is in the vacuum range, although it's not, I guess you'd say it's like an 85 kilopascal vacuum. And you can see that it's still partially steam. It's 90% quality. And then at 4 right here, we get what the pump is doing before it goes to the pump. So this is out of the condenser. And there's a little bit of a pressure drop, but there's going to be a significant drop in enthalpy that happens right there. So it goes from 2,361 to 188 across the condenser, which is an important thing. All right, so that's the setup for the problem, and we're going to break this thing down into these different processes, right? So we're going to go from state 1 to state 2, and then state 2 to state 3, state 3 to state 4. It didn't tell us to do it, but we could do state 4 to state 5, and then we could go state 5 to state 1, right? So state to state to state to state. These are different processes, and adding them together, we make a cycle. So the main equation, I'll put it up at top because I didn't leave a lot of room up here. Here's the main equation. We're going to do it on a per mass basis, so it's going to be the same equation basically that we've been doing, right? So here's we could have we're going to use lowercase q minus lowercase w plus hi minus h exiting. Right, so that's like our basic conservation of energy equation, but on a per mass basis. So for this thing A, going from state 1 to state 2, go 1 to 2, we're going to say 0 is equal to Q 1 to 2 minus W 1 to 2 plus HI minus, it should be H1 minus H2, right? So that's the I and that's the E. No work is done between these two states. We're only going to have this guy coming out. So we're going to have Q1 to 2 is going to be equal H2 minus H1. And so what we have, H2 is 3,000 2.5 minus 3,023.5, or equals to a negative 21. but that's expected to be negative because we are losing heat. This equation at the very beginning is all assuming that we have heat in and work out. That's the generally accepted type of scenario that happens. Although there's many situations where they don't, and this is one of them. All right, so this actually answers the heat transfer in the line between the boiler and the turbine. The heat transfer in the line, and they say between the boiler and the turbine. They don't mean that the heat transfer is being transferred between the boiler and the turbine. They mean the line is between those two. The heat is being transferred up into the, let's say, the engine room, making the engine room hotter. Right, so H1 to 2. All right, so B is going to be the turbine work. All right, so we're going to go between 2 and 3. Let's make a good habit of thinking our way through the problems and what each of these things are. Plus H through 2 minus H3. All right, we're accounting for all the heat. Well, there could be heat transferred here if there was perhaps this didn't have good insulation around it. But we're going to pretend like it is well insulated and the heat is not allowed to escape. So there you go, well insulated. So we can say that W2 to 3, bringing him onto the other side of the 0, is going to be H2 minus H3. And so H2 is 3002.5. And we're going to subtract out H3, and they already did that for us. They already did look this up at these conditions, right? So they had that pressure, and with this quality for saturated, we got this amount. So that's how much enthalpy is at that spot, 2,361.7. So you get 640.8 kilojoules per kilogram, and so that's the output. And the whole point of the cycle is to get that work right here, that work output, that shaft work. But unfortunately, in order to get that, we have to throw some heat away. Now we're gonna bring this up many times, but the most ideal engine, or the idealization of an engine, is to have a heat source and a heat sink. And between those two things is what are needed to be able to make what we call sometimes a heat engine. And this qualifies as a heat engine, as I guess most do in one way or another. So we have a source and we have a sink, and we have to have that. So we have to throw some away, unfortunately. So we have, right out of the equation, this time is going to be between 3 and 4. So Q 3 to 4 minus the work 3 to 4 plus the heat 3, not heat, enthalpy 3 to 4. I didn't mean to say heat. Yeah, this is the heat. There's no work going on here, so it's going to be 0. And so we're going to go the Q34 is going to be equal to, because I had to bump it onto the other side, it's going to be H4 minus H3. So the H4 is going to be right here, 188.4. And then minus, and the enthalpy we just said was 2,361, so 2,361.7. And that's going to be negative to represent the fact that it's heat lost, and these are kilojoules per kilogram, or heat out, maybe I should say. And we don't necessarily it's lost. I mean, it didn't just disappear. We know where it went. We just can't get it, and we can't do anything with it. So for D, okay, so I went ahead and did an intermediate step here because I like doing things completely if I can. Let's go from 4 to 5. Now they went ahead and they told us, and I didn't read it, so let me go back and read it, that the pump added 4 kilojoules per kilogram worth of work in there. So that was between numbers 4 and 5. So the heat between 4 and 5 minus the work between 4 and 5. And that's going to be the pump, by the way, putting stuff in. And I think we do have, I think I do have to make it negative. Yeah, I think I do. Oh, I know what I know why I did this. Okay. Plus 4 coming in minus 5 going out. We're going to assume that we don't have any heat transfer taking place. And what we'd like to know is what is H5, right? So we were given H5, but we were given this right here. So what we could do is say 0 equals minus, because that's a minus, but a minus 4 kilojoules per kilogram plus, what's H4? H4 is going to be our 188.4 minus H5. And so what we're going to find is that H5 is going to equal 192.4 kilojoules per kilogram. And so this is how much, this is the result of the pump work, right? It increased the enthalpy because we added work in. And remember that negative, we added as a negative because it was, I know it's weird. And then, okay, so then the last one, D, we're going to see what the boiler does. And so that's going to be Q 5 to 1, which always makes it weird, right? It's going to be the W 5 to 1. 5 is going to be the input. 1 is going to be the out. So there's no work going on in the boiler. And so we could just write out this Q 5 to 1. Let's bring these on the other side. It's going to equal H1 minus H5, or the H1, as we were told in the beginning, was 3023.5, right? Like right here. And this was 192.4. So you get 2,831.1 kilojoules per kilogram. Now, if you think about it, that's not a very good deal because we paid this amount in heat, but we only got this amount in work out when it came to the actual deliverable that we wanted to get out of it. And the whole point of this thing was not just to play around and heat up water, make it steam, but to make this thing go around and generate stuff. So we will see soon that we often want to talk about the efficiency, which a good friend said, what you want over what you paid for. What you want. And what we wanted was 640.8 kilojoules per kilogram. But we paid for it not only 2,831.1, but we also somehow magically got 4. We had to pay for it with this too. So that's not the only thing to be concerned with. And if you take it and do calculate that, you get 21.2%. And that is not a very good efficiency at all, but it's realistic actually. We could do a whole lot of things to improve it on steam plants, something we've there's been a lot of effort been done on a bunch of different ways to improve the cycle, and makes it way more complicated. But that kept me employed. That it was way more complicated. So another example done, and I will see you again in the next example, which is a refrigerator with a compressor. Exciting. I know you're looking forward to it.